The neatest thing about Isaac Newton's Principia was that it gave a mathematical basis to things we already knew about the universe. Johannes Kepler had spent decades studying the stars, and his boss, Tycho Brahe, had as well. And he came up with some laws on how planets move. And one of the interesting ones was the relationship between how far a planet is from a star, the radius of orbit, and how long it took for it to complete the orbit, which is called the period. And Kepler was able to determine that the period squared was proportional to the radius cubed. Why? It took until Newton's laws and Newton's theoretical basis to explain that. We're going to derive the relationship for circular orbits, and it requires nothing more than our understanding of the law of gravity and our understanding of circular motion. In this class, we're going to limit ourselves to the special case of circular orbits. The Earth's motion around the sun is not quite a circle, although our ellipse is pretty close to circular, so we can get a good idea of how Kepler's third law works by pretending it's a circle. We've got the Earth orbiting the sun. We know there's a force of gravity acting inwards, and that's our only centripetal force. You've already drawn a free body diagram like that and solved a problem closely related to this back in our circular motion unit. And here's the problem. I'd like you to take a second, pause the video, go ahead and try to solve this problem again, see what comes back from circular motion. And then we'll use the ideas in it to try to figure out how period and radius are related. All right, welcome back. Hopefully you got a really big number, 3.58 times 10 to the 22. Relatively simple sigma f equals ma problem. We just plug in fg. The acceleration, of course, is v squared over r since it's circular motion. And the other little trick from this problem was that we assumed that if we're moving in a circular orbit at constant speed, that the velocity is the circumference divided by the period, or 2 pi r over t. This is only valid for a perfect circle. If you have an ellipse, you get closer and farther from the sun. And we'll see another one of Kepler's laws shows that you speed up and slow down when that happens. But it's a ballpark approximation for the Earth's orbit, which is elliptical, but not that far from a circle. What we're going to do now is not plug specific numbers in. We're going to leave these as letters, and we're going to try to derive an equation that ultimately relates r and t. This will be called Kepler's third law, and it'll help us understand how your distance from the thing you're orbiting affects how long it takes. What we now need to do is we need to sub in the force of gravity. So the equation for the force of gravity is going to be Newton's law of gravity. So it'll be big G m1, m2. Well, in this case, it's the mass of the Earth and the mass of the sun. And that's over r squared. And that all is still equal to me v squared over r. So we can see that a bunch of stuff cancels here. If we multiply both sides of this equation by r, we see that this goes away and that this term is canceled. And we also see that the mass of the Earth is on both sides, so we can divide it out. So what we're left with now is G mass of the sun over R equals v squared. So our goal for all of this is to come up with an equation that relates how far you are away from the thing you're orbiting versus how long it takes you to orbit. In other words, relating the radius to the period. And whenever we get that equation, that'll be called Kepler's third law. But this equation is actually kind of a useful intermediate step that we can use to solve interesting problems. It turns out there's a certain speed you have at every distance from the thing you're orbiting. So we can use this directly. So I'd like you to take a minute and try to solve this problem. We have our Hubble telescope which orbits the Earth. I'd like you to tell me how fast it's going. So things you need the distance it orbits from the center of the Earth. You need the mass of the Earth. And then you need big G, which is what it always is, 6.67 times 10 to the minus 11th. So go ahead, pause the video. All right, so welcome back. So we have all that work we just did to get the equation for v squared. Of course, if we square root it, the equation ends up being like this. We just plug in those numbers, and that tells us how fast something is going if it's a particular distance from the Earth. So that's a useful expression in itself, and it's one that you should feel free to use if you have questions like that. What we're going to do now, though, is find an expression for v that we can plug in here, and that's eventually going to get us our relationship that we're looking for, the relationship between time for an orbit and distance from the thing you're orbiting. It's an equation you know pretty well. We know that the velocity is distance over time. So what's the velocity? In this case, it's the circumference over the period, or 2 pi r over the period. Now we're set to see Kepler's third law. We'll plug this velocity in. So we get g mass of the sun over r equals this velocity squared so g ms over r is 4 pi squared r squared over t squared. We're almost done. I'm going to cross multiply. So I have t squared g ms is equal to 4 pi squared r squared times r. That was my cross multiplying. And then I'm going to divide both sides by GMS. And what I'm left with is Kepler's third law. So I'll write that up here. T squared equals 4 pi squared over GMS. R squared times R is R cubed. And that's Kepler's third law. The square period is proportional to the cubed radius. I know that was a lot, but it's so important because Kepler's third law didn't come from anything you see in this picture. It came from Kepler and Brahe watching the sky for decades and seeing how how planets move. There was a relationship between how far they were from the sun and how long it took them for an orbit. And radius cubed was proportional to period squared. The why for that didn't come until later. And you could see all of the separate ideas of Newtonian physics that we've combined here. Sigma F equals ma.
Circular motion. Acceleration is v squared over r. Newton's law of universal gravitation. We put together so many pieces we already knew, and it seemed like a bunch of math stuff, but we came up with something that's actually how planets behave. And that's pretty special. So we derived this for circular orbits, but it can be generalized to elliptical orbits as well, and it's a really important rule of nature. Let's use it to solve a problem. So we'll go back to our Hubble telescope, and this looks similar to the problem we did earlier in the video, but it's a little different. Now it's not asking for speed. It gives us the distance from the Earth, and it asks us to predict how long it takes to complete an orbit. So go ahead and use Kepler's third law and see if you can answer this question. Pause the video and come back when you think you got it. All right, welcome back. So all of this is just the derivation of the third law again. Here it is. And everything in this fraction is just constants. And it gave us what the radius was. So we should be able to solve for the period. And we end up with 1.59 hours. And that is really close to the actual orbital period of the telescope, which is 97 minutes or 1.61 hours, according to the European Space Agency. All right, so now we've derived Kepler's third law mathematically, and we've seen that it was observed astronomically. There's just one other thing worth mentioning. You'll notice sometimes I put the sun in the middle and had a planet orbiting. Sometimes I put the Earth in the middle and had a satellite orbiting. It works in both cases. So we'll use it with the planets orbiting the sun, satellites orbiting a planet, and moons orbiting a planet.